Okay, welcome. This is Chapter 4, Network Access. This is for my Introduction to Networking or Networking Fundamentals class, depending on which class you're in. So, the objectives for this week is we're looking at layers 1 and 2, physical and data link, and medias. We're going to describe some of the characteristics of the layers and our mediums. We're going to talk about the physical layouts of our topologies. We're going to describe how we do controlling mechanisms for our LANs and WANs, again, at the physical layer. Maybe also discuss our layer 2 or our frame headers and footers. That way we can understand the structure to our frames. So our first part is media access control, and that's broken down into 4 major sections: physical, network media, data link, and media access. So here we're taking our data link and we're doing both sublayers, media access control and the LLC. However, we're not doing the LLC currently in this lecture. That's going to be saved for a later lecture. So let's look at the first one, our physical layer protocols, and that's going to be what's happening at the wiring aspect. Here we have a small office, home office, or SOHO router, and this is actually a router, a switch, and a wireless device all combined into one. So if we're hooking this up for internet usage, how do we do that? How do we hook it up? How we do that is by connecting a cable from our node, our computer, our laptop, whatever, to one of our blue ports or LAN ports. And from the yellow port that's labeled internet, we're going to have that wired to either a DSL modem or cable modem, and that will provide our access to the outside. If we're talking Wi-Fi, we could just be connecting it via our wireless cards. And that could also be wireless cards with range extenders, where we have one router, and from that router, we have range extenders that will then extend the range of that wireless device. That way, throughout our entire facility, we can have wireless access. Okay, we are dealing with the physical layer, the bottom layer, and that's going to be transmission in bits. If we are looking at some of the physical medias, that's going to be either copper, fiber, or wireless, or microwave. We could see the different types of signals. Copper is going to be electrical, fiber is going to be light pulses, and some type of wireless should be microwave signals or radio frequency signals. So some of our standards for our physical layer and the different types of organizational bodies, ISO, they lay out certain standards like ISO 8080 or 8877, and that's the RJ connector type. So within our physical medias, the RJ11 and RJ45 is dictated by the 8877 standard, just like the wiring pattern, IATF 568, that is dictated by the ISO 1181 standard. IATF has several of their own standards. For example, TIA 598C, that's the fiber optic color coding. If we're talking ITU, that could be the ADSL, the G992 standard. If we're looking at the actual pinout for our RJ45s, that's going to be our ANSI 568C, and that's co-developed with IATIA. If we're looking at some of the IEEE standards, that could be 802.3, that will be our Ethernet, which is our common methodology for transfer for data networks. 802.11 wireless, 802.15 Bluetooth, 802.16 WiMAX, and so forth. All right, some of the advantages or other characteristics for our cable types. If we're dealing with copper, we are looking at electrical magnetic changes. So that's the intensity of a electromagnetic field or the phase. We could be talking about encoding. That could be Manchester encoding or non-returning zero techniques or 4-bit, 5-bit. If we are looking at the physical components, copper cable should be a twisted pair or coax. If we're talking fiber, we're talking single mode or multi-mode, and that's pulses of light or the wavelength being multiplexed, different colors. The signaling methodology there is pulse or no pulse, very similar to a electromagnetic pulse. There is it not. Wireless is going to be an access point, maybe radio or an antenna. And there are several different types of encoding techniques here. Frequency hopping is left off, but we have DSSS or direct sequence spread spectrum or our OFDM. All of those signaling methods for our wireless are radio waves. So let's talk about bandwidth. Bandwidth is the theoretical maximum capacity of a medium. Everything is measured in bits per second, BPS, little b, not big B, but little b, and everything is times 1,000. So from bits to kilobits, it's bits times 1,000. From kilobits to megabits, it's kilobits times 1,000. From megabits to gigabits, times 1,000, and from gigabit to terabits, 1,000. Each step increase is times 1,000. Again, if we're measuring transmission, we're normally measuring in bits per second. Throughput, however, is vastly different from bandwidth. Throughput is the actual amount of data going through the wire. Because again, when you send something, there is overhead. So throughput is different from the theoretical maximum. If we're looking at types of physical media and we're looking at a router, we could be talking things like HDSL. We could be talking about some type of management port, USB. So on a modular Cisco router, things could be different. Moving on to our network media, we've already talked about certain characteristics of copper being electrical signals. And here we have a real signal. You can see it go to 3 volt, and each time it's a 3 volt signal, that represents a 1. The absence of the voltage represents a 0. But what happens when there's interference? And then we have digital signal with interference. You can no longer tell if it's with or without voltage. And then once the computer reads it, we may be getting false readings because of noise. Some of the copper media, which we already talked about, twisted pair versus coax. Twisted pair comes in 2 flavored, unshielded and shielded. And then coax is just regular coax. For our twisted pair, if we're looking at our unshielded twisted pair, it is just a specific amount of pairs that are twisted together. This is here 4 pair, each pair being twisted together in a specific way, and it's color coded. STP is our individual pairs being shielded, and then all of them being shielded a second time. If we're looking at coax, pretty similar. We have a copper core, then we have one layer of shielding, and then another layer of shielding. Now, the first layer could be just plastic insulation, and then it could be tinfoil or copper mesh, either or. Common types for our coax could be our BNC or our twists, N-type and F-type. N-type's not really that common. BNC and F-type are very common. Copper media safety, because there is electricity going through it, we need to make sure that data and electrical power cabling is meeting all safety codes. It's installed properly, as well as inspected. And lastly, that the equipment is grounded correctly. That way we don't have power going through equipment that it shouldn't be going through. Moving on to some of the basic properties. is UTP cable does not use shielding to counter the effects of EMI or radio frequencies. So instead, the cable designers have discovered that they can limit the negative effects by crosstalk, by cancellation, as well as by varying the number of twists per wire. So in this example, you'll notice the blue and green have more twists than the red and brown. This is done so that crosstalk, or the jumping of signal between one pair and another, can be mitigated. Twisted pair come in different types of standards, like 3, 5, 6, and 7. 5 and 6 are the most common. 3 is you can still occasionally find. Not normally used for data, but does still exist. And 7. 7 is shielded twisted pair, and it's not as common, but can still be found. Cat 6 is normally for gig or 10 gig, and 5E is also used for gig. It can transmit up to 100 meters. The way that the UTP or STP are terminated are by an RJ45 plug or by an RJ45 socket. There's a specific color code to these. That color code comes in two flavors, T568A and T568B. Why the two? Because there's two different types of cables, a straight through and a crossover. A straight through is one cable with the same connector pattern on both sides. So for example, we could have T568A on both sides, that'd be a straight through. Or we could have T568B on both sides, and that's a straight through. Straight through connects most devices. However, we have a crossover cable with the cable being made with T568A on one side and T568B on the other, and they connect like devices, computer to computer, switch to switch, router to router. All of those are used or using a crossover cable. Lastly, we have a rollover cable, which is used for connecting a PC to a router for the purpose of configuration. If we're looking at the A and B pattern, you'll notice that the only difference is the pins 1, 2, 3, and 6, because they are flipped. On A, it's white, green, green, with on B, it's white, orange, orange. The 1, 2, 3, and 6 are flipped between the two. And you'll notice that pins 4, 5, 7, and 8 are the same on both patterns. After you make the cable, we have to test them. Normally we test them for length, signal loss, as well as crosstalk. Moving on to fiber, some of the properties and where they can be used at could be things like fiber to home, fiber to the curb, fiber to the office, maybe enterprise networks, long-haul networks, or submarine networks. Submarine, that's normally underwater. Long haul is a big one. Between Las Vegas and Reno, there is dark fiber between both cities. And as they've been laying the fiber between both cities, they've been stopping at communities to allow them to connect to that long haul fiber. It's made to go the distance. What is the fiber made out of? It will have a center core, whether it be glass or plastic polymer. Then it will have a cladding around it, then buffer, then some type of Kevlar, then an outer jacket for strength. Our fiber optics come in two flavors, single mode or multi-mode. Single mode, the center core is about between 8 and 9 microns thick, where the multi-mode is roughly 6 to 2.5 microns thick. And that's just the core. Not always the glass cladding, but just the core. The reason that's important is because single mode smaller core, it can go the distance, it can go farther, and is normally powered by a laser. Multi-mode, while it can go the distance, it doesn't go as far as single mode, and it's normally powered by an LED. Common types of connectors are ST, SC, and LC. Those are the three common types. ST, very similar to our BNC, they're a twist plugin. SC are just a straight plugin, and LC is just a straight plugin. They will always come in pairs, one for sending, one for receiving. If you are terminating them yourself, we have to know how to test them. We test them with a optical time domain reflectometer. That will give you if the distance, it will give you if the cable is good, or if the cable is damaged, it will tell you exactly where the damaged part is. Pros and cons for fiber versus copper. Copper is cheaper. Copper takes less skill to install. Fiber is more expensive, but it's more skill based. Copper is affected by EMI and radio frequency. Fiber is not. Copper has electrical hazards because it can shock. Fiber does not. Media connectors. Fiber is more expensive. Copper is cheaper. Installation. Fiber requires more skilled labor. Safety. Safety is good for both of them. Some of the properties for our wireless. One of the big ones is converged. This is also an area of concern. Meaning, if you have a building, it's a hallway, and you have an antenna on both sides, this network should not be like building north, and this network should be building south. No. What should happen is these two antennas should communicate with one another. That way, this could all be the same network. So as you walk between access points, the access points themselves hand you off to the next one, thus allowing you to have a converged network. Other areas is security. You can actually secure Wi-Fi so that it is fairly secure. Radius servers. Types of wireless could be Wi-Fi, Bluetooth, WiMAX. Some of our wired standards could be the 802.11 standard. It's very important to know the speeds and frequencies for A, B, G, N, AC. So for A, we're talking 54 megabits at 5 gigahertz. For B, we're talking 11 megabits at 2.4 gigahertz. With G, you're going to notice the speed went back to 54 megabits, but however, the frequency is 2.4. With N, we're looking at 600 megabits at the 2.4 and 5 gigahertz. With the 802.11 AC, we're looking at 1 gigabit at 5 gigahertz. Bluetooth is normally 3 megabits, and WiMAX speeds may vary depending on distance. WiMAX is 802.16. Here's what a SOHO router might look like. Here are our speeds again and our frequencies. Moving on to our data link layer protocols. This is layer 2. Now, how does data link actually stack up? We are looking at two sublayers, the MAC and LLC, and you'll notice Ethernet, Wi-Fi, Bluetooth, WiMAX, all of these operate between the physical and the MAC sublayer. So the data link layer protocols govern how the formatting of frame and how the different medias affect that frame. The MAC sublayer also provides access to the media. So let's look at how we format data for transmission. We take a layer 3 packet and we attach a header and trailer to it. The header starts with a start frame, some addressing, and some other general information for the header, and then it sends it to the data. Then at the very end, we have some type of frame check sequence used for error detection and a frame stop bit. For our creating a frame, again, we take our packet, we put on the header, we put on the trailer, and that's how we get it. Different types of standards for our data link wiring could be our 802.2 LLC, 802.3 our Ethernet token ring. I mean, you could read down the list. Other types of data link layers that are not very common could be our HDLC or our Fiber Distributed Data Interface or FDDI, WiMAX, Bluetooth, ADSL, ISBN, Frame Relay, MPLS. Those are all very common ones. So controlling access to the media, the important thing here is how do we communicate when we are sharing a media, and that's what's coming up. But before we get to that, let's talk about our physical and logical topologies. And our physical topology is going to be the actual physical wiring. How's the wiring ran? As opposed to our logical, which is going to be more of our addressing scheme. How do our computers connect via our addressing scheme? Some common physical WAN topologies could be a point-to-point, hub and spoke, or full mesh. If we are connecting to our ISP, between us and the ISP could be a point-to-point, but realistically our ISP is not just serving us, so it could be more of a hub and spoke. Examples of a point-to-point could be two different locations going through a network. Though a logical point-to-point could be, again, similar. Two nodes, a source and destination, going through like the internet. We have half duplex and full duplex, meaning we can send or receive, that's half duplex, or we can send and receive, and that's full duplex. Physical topologies could consist of things like a star or extended star where we combine two stars, maybe a bus, maybe a ring. We're going to come back to this though. So our logical topology is going to be contention based or control based. With contention based, stations can transmit at any time and collisions will exist. And there are mechanisms in place to help resolve these issues. Carrier sensing multiple access collision detection, CCNA CD, is used for our Ethernet. While if we're using wireless, we could be using CCNA collision avoidance. And again, that's used in wireless. And those are the rules that are set forth that govern what to happen when a collision occurs. Here's an example. In our logical multi-access topology, computer E needs to transmit. It will check for other transmissions. If none are detected, it will transmit. That's different if we're using controlled access. Controlled access, you have to have a specific token to communicate. So you have to take turns. And that could be things like token ring or FDDI. Because again, it's a ring topology. And so if D wants to communicate, it has to go around the circle. And everyone gets to see what's being transmitted. The frame could come in two different ways. A fragile environment where protection may be needed, or in a protected environment where it may not. Meaning, if we need to make a greater effort to make sure that it's delivered, then it's higher overhead, which means it's slower. And that's true for fragile environments. If we need to make sure it's going to get delivered, and the fragile environment, we may need to stick additional stuff there so that it's guaranteed to actually be delivered. Looking at our header, again, we have our start, our address, our type, our data, our frame check sequence or error checking, and then our stop frame. Here's a multiple access frame and has minimal possible destinations, and it could go to each PC if we're not using the appropriate technology. We've already talked about our trailer being our frame check sequence. Again, that's going to use for error checking, and our stop frame. Here is our LAN and WAN frames because again, the different types of technology that are being used could be different. Like, are we using HDLC, frame relay, MPLS, PPP frames, Ethernet frames? All of these frames may be different. Ethernet's the most common type, but again, it varies. Within an Ethernet frame, we have a preamble, which is used for synchronization. It also contains a delimiter to mark the end of the timing information, source and destination info, types, data, and error checking. While if we're using a PPP protocol, we slightly different. It's a flag address control protocol, then the data, and then our error checking. Notice address is no longer source and destination. Because it's point to point, it's just going to assume destination. No source will be included. Next is our wireless. Our wireless again uses CCNA collision avoidance, and this frame is slightly different. This frame will use a frame control, which will have things like protocol version, type, subtype, from and to, additional flags, retries, power management, data encryption, and so forth. And that's actually it for this chapter. I want to thank you and hope you guys have a great day.